Okay, we're going to look at problem 11 in chapter 4, in the chapter 4 assignment. And I'll tell you up front that this is a Bayes theorem problem. But the question is, how do you recognize it as a Bayes theorem problem? How do you set it up and solve it? Now, your textbook presents several methods for doing this. I'm going to demonstrate just one, which is called the tabular method. Well, let's take a look at the problem first. We have a firm that submitted a bid for a major research project. Now, management estimates that they have a 50-50 chance of winning the bid for the project. But the agency to which they've submitted the bid has subsequently requested some additional information. They've asked for some additional information. Now, this is where the key to recognizing it as a Bayes theorem problem comes in. We've got some past experience that indicates that for 79% of the successful bids and 44% of the unsuccessful bids, this agency has requested additional information. So this is the additional information in the problem that should trigger you to recognize it as a Bayes theorem problem. Now, I'm showing you the answers to each of the questions that they ask, but then we're going to look at how they came up with those answers. The first question is, what is the prior probability of the bid being successful? And they told you up front they felt they had a 50-50 chance, so the answer to that is simply 0.5. Then they asked, what is the conditional probability of a request for the additional information given that the bid will ultimately be successful? So they're kind of guiding you through the problem here. And the answer to that is 0.79. That was the 79% of the successful bids, given that there were some additional information requested. And I'll explain what that conditional probability is. And ultimately, you have to compute what's called a posterior probability. And this is the probability that results from having that additional information. So I'm going to pause here and shift to the actual setup of the problem. Okay, so as I said, I'm going to set this up manually before we do anything on Excel. So we have two events, where W is we win the bid, L is we lose the bid, R is the request for more information. So the probability of winning is 0.5. The probability of losing is also 0.5. These two events are mutually exclusive. You either win or you lose. We're given some information, and this is the tricky part, that the probability that additional information was requested, given that they were winning bids, was 0.79. And the probability that additional information was requested, given that it was a losing bid, was 0.44. Now, this information comes from historical data. This is not something you could derive. You would actually have to have historical data about previous bids to know these probabilities. And that's the key. One of the keys to recognizing it as a Bayes theorem problem. There is some additional information that you're given from history that lets you set up these probabilities. And the only clue in looking at these problems as to how these conditional probabilities should be set up is that it's going to be the opposite from the ultimate posterior probabilities that you're trying to compute. So what we want to know in the end is, what is the probability that we win the bid given that additional information was requested? And what is the probability of losing the bid given that additional information was requested? Now, as I said, there are actually three different methods you could use to solve this problem. One is the probability tree, which is laid out in your textbook. The other is a formula that's also derived and laid out in your textbook. But I'll be honest with you, I think both of those methods are a little cumbersome and a little bit harder for most people to understand. But work through those just to see how they're done. What I'm going to show you is the tabular method, which I feel is probably one of the more straightforward ways of doing this. So now that we've determined these probabilities, let me show you how this could be set up. We start with the event of winning, and we have a prior probability, and we have the conditional probability. And using the multiplication law, that's also discussed in Chapter 4, we know that if we multiply the prior probability times that conditional probability, it gives us a joint probability. So the 0.5 times the 0.79 gives us the probability of additional information and winning, which is 0.395. Likewise, the probability of losing is 0.5 multiplied by that conditional probability of additional information given that the bid was lost from historical data of 0.44. We multiply those two together, we get the probability of additional information and losing of 0.220. Now, both of these joint probabilities involve the event of additional information being requested. And these are the only two ways that additional information can be requested. Either additional information and we win, or additional information requested and we lose. So if you add both of those probabilities together, you get the probability of additional information being requested. So adding these two values, 0.395 plus 0.220, gives you a probability of 0.615 as being the probability that additional information will be requested. So now we can use this to compute the posterior, or what is sometimes called the revised probabilities. So the probability of winning, given that additional information was requested, is going to be the probability of W and R divided by the probability of R. In this case, 0.395 divided by 0.615, or 0.642. Likewise, the probability of losing, given that additional information was requested, the probability of L and R divided by the probability of R, 0.220 divided by 0.615, or 0.358. Now, both the posterior probabilities added together are also mutually exclusive, so they must add to 1, just as the prior probabilities are also mutually exclusive, so they have to add to 1 as well. So that's the tabular method for solving the problem. So I haven't shown you how to do this manually, and you can do these manually, it's not very complicated. I do have a Bayes theorem problem worksheet in the statistical toolkit. Now, yours is going to look a bit different than this one because I've actually cleaned this up a little bit and left only 2 of the tables. The toolkit that you downloaded may have more than 2 of these tables, but the principle is the same. You can actually delete any of the extra tables and leave the one that simply has 2 events, and there's another one there. There are actually multiple that have more than 2 events, but the principle is the same. We have the prior probabilities, which in our case are 0.5, I've simply added everything in the prior probabilities column to show that that should add to 1. We have the conditional probabilities, in our case 0.79 and 0.44. And for these, you only need to put the information in the green area. Everything else is calculated. So the joint probability again, 0.395 and 0.22 for the total. In this case, B represents our R variable of additional information. The A variable represents our events, where A1 is winning and A2 is losing. So then it calculates the joint probabilities and then the posterior probabilities in each case. So same values, especially to 3 decimal places. And actually, in the problem, they ask for the probability of winning, given that there was additional information, to 2 decimal places, which gives you the 0.64. So as I always say, the key to any of these probability problems is simply to do multiple problems so that you can get used to seeing how they're set up, how they're worded. And the wording, unfortunately, of Bayes' theorem problems always seems to be a bit cryptic. But with repetition, you start to recognize when the conditional probabilities for the additional information is being given. So again, practice.